My name is Grant Ingersoll. This is Ted Dunning. I wanted to start off by asking some questions, and then we'll get into some of the details of what we mean about reflected intelligence, how all of this stuff kind of starts to work with search and big data. And the first question I'd ask, well, gee, you know, you're at a search conference. This is Lucene and Solr. Is search enough, right? In many ways, the Lucene and Solr projects have pretty effectively commoditized keyword-based search, right? So how many of you actually are just doing pure keyword search, no other signals whatsoever go into when users come in and ask a question? Anybody? Anybody just doing basic keyword search? Okay, so a couple of you. How many of you are using maybe a handful of other features, maybe user profiles, clicks, anything like that? So some more hands go up. So when you actually look at like internet search, for instance, this is a cool fact I learned last year at the Special Interest Group Conference on Information Retrieval. The search giants, the Googles, the Bings, etc., they use somewhere between, by most estimates, somewhere between 500 and 1,000 different features just to calculate relevance, right? Keyword search is one of those, or a few of those, right? And so you start to ask this question, well, is search enough? And really what you then end up logically coming to is you need a much more holistic view of not only your data, but also the way users are interacting with that data. And that is at the heart of what we mean by reflective intelligence. When you can start to bring in all of these other kinds of signals that you have in your system and bring that in to make search better. And really, the things that you start to do then is you kind of need this combination of search, discovery, and analytics to really bring all of these things together. Search is really great when people know more or less what they're looking for and you can guide them a little bit. Discovery really helps with that kind of giving the users that gentle nudge of, hey, you know, did you mean this? Or other people thought that. Maybe you should go check those kinds of things out. And then the analytics is really what powers the back end, what helps you guys really understand what your users are doing. It helps your businesses translate that into more money, time saved, all of those kinds of things. And so that in our mind, in working with Ted over the years, is really the key to unlocking the real value in not only your data, but also in your users. So just a little bit of background. I think most people here know me. I'm the CTO at LucidWorks, also one of the co-founders of Mahout, and been doing Lucene and Solr and this machine learning stuff for a number of years. And then Ted, if you're not familiar with Ted, Ted's been doing this stuff for a long time as well. It turns out after a while you've been in search long enough that you kind of overlap. That's the case for Ted and I. Been doing a lot of great things in the past, music match, VO networks, etc. So what we're going to try to do in this talk is draw in all of those things. Ted is, of course, now the chief application architect at MapR. They're one of the leading Hadoop distributions out there. If you're not familiar with what they're doing, we're going to talk about how we do all of this stuff in the context of the things in our day jobs, if you will, as well. So a little bit of the agenda. Obviously, we've got some introductions out of the way, and then we're really going to talk some more about some of the search revolution that's going on, how that plays into this reflected intelligence piece, and then get into some of the use cases, and then we'll finish it off by looking at some reference architectures and implementations around these things. And then hopefully at the end of the day, you'll leave with this notion that by combining all of these things, you get a lot more than just adding one and one. You get more than two, you get three. So. With that,
keep going.
Well,
tell her.
Okay.
You're tall.
So we need to really get a second microphone. So when you start to think about users' interactions with big data, it kind of can break it down into a few things. Most of you in this room probably fall into one of these two categories, right? There's the system administrators. They're often just taking care of the DevOps sides of things. What's going on with the file systems? What's going on with the indexes? Where are they replicated? Who's up? Who's down? All of that kind of stuff. And then, you know, us as search engineers, if you will, we're really digging into what's actually going on with the data, how are people accessing that, the key value stores, what kind of query languages do we want to be exposing to people, so on and so forth, how are we tracking relevance, etc. And then last but not least, there's always these pesky users, right? The people who pay the bills, but they really annoy you as an engineer in many ways. These guys are where you really start to need to change your opinion about, because in many ways, getting beyond keyword search really means leveraging what they're doing. So with that, I'm going to hand it off to Ted, and we'll just stand by each other.
I thought we were going to do a Penn and Teller sort of thing. I would get to stand and do something comical, but now I have to say something and do something comical. Much harder. So what we want to do is down here in that lower right corner, we want to add the idea of reflected intelligence. And reflected intelligence is a pretty simple concept. It's a simple metaphor. But the basic idea is that the whole idea of artificial intelligence from the 30s on missed one really important point. The definition of that has always been Turing's definition. If a person can talk to a computer and they can't tell it's a computer they're talking to, then the computer seems intelligent. But there's an implicit assumption there. The assumption is that there's one person talking to one computer. And the obvious extension of that people thought about for a long time is there would be 1 million people each talking to one computer. And that's absolutely wrong in the common world. What happens is we have 1 million users talking essentially to one computer. That's called the internet. It is one computational device, connected, disconnected, reliable, unreliable, and things like that. But having these 1 million people talk to the same system means that if one of them does something very clever, we can reflect that cleverness back to another user via the system, and the system now appears as clever as the first user, as long as we do it in the right context and changing the pronouns. So, instead of saying they, we say we suggest. So instead of this user in Ottawa being very clever about music and figuring out what you in Iowa want, we say we suggest that. We reflect that intelligence, make something that appears to be intelligent. It's vastly easier than building a truly intelligent, an artificially intelligent system. And we're going to talk a bit about some examples of different ways we've done that together with LucidWorks, with MapR, with some of the stuff in my background, and how together we can build these systems with a MapR LucidWorks combined system. Good name on this slide.
So in case you haven't noticed, you're at the Lucene Solar Revolution. And in case you haven't noticed in the past few years, there's a revolution going on in search, and it goes well beyond just the open source part of it, right? In effect, what we've kind of coined a term around, Ted and myself, is that there's a lot of abuse going on around search, and that you start using search, and it very quickly leads to search abuse. Tim Potter earlier on in the session actually kind of alluded to this when he said Solr is addictive. The business people get used to this stuff. They start crunching more and more analytics out of their search engine. They're powering more and more of things that have nothing to do with search in the traditional sense of keywords in a text box. That's what we mean by search revolution. Because what's often happening is when you start to look at the problem of search or how we solve search, Lucene's a great example. If you just care about from a pedagogical standpoint, you can go in and figure out how people build real search engines by looking at Lucene. You can start to see that there's a lot of really interesting data structures in there, and there's a lot of really interesting algorithms in there. And hey, we're all computer scientists, or most of us are. Why don't we use our computer science brains to leverage these things to solve common problems beyond just the text box? So for instance, I think my mind was blown by Ted a few years ago when he said to me, oh, well, search is just a really fast, sparse matrix multiplication. And like most things that Ted says to me, it occurred to me about 4 days later what he meant by that. And hopefully you'll go home and it won't take you as long as it did me. But at the end of the day, that's what Lucene is doing underneath the hood. And there's a whole class of problems that can be solved by sparse matrix multiplication, where something like Lucene, Solr, etc., can really solve those things. So things like recommenders, etc. We'll get into some more of these use cases. Now, the other part of the revolution really is around Lucene and Solr. And what you've been seeing there is more and more usages of that go well beyond that text box. So my career with Lucene, I actually started building a cross-language information retrieval system. You put in English, you get back Arabic documents, and hopefully you have like machine translation in there. You can imagine who was paying for that search system. But it was very much straightforward search. And so I started needing some things in Lucene. I started contributing back patches, and then like the idiot that I am, they go and make you a committer, and then the rest is history. You have to now go commit your own patches, etc. But the interesting thing that started to happen along the way is you'd see these people on the mailing list saying things like, I want to use Lucene as a key value store, or I want to use Lucene to build a recommender engine, or I want to use Lucene to do classification. And I'm sitting there at first thinking, well, gee, that's not really what this text-based search engine is all about. But you know what? When you start to look at the math underneath the hood, it actually can kind of work out that way. And so you start to see this revolution going on. You also see it, particularly in Lucene 4, et cetera, that there's a lot more things like database-like features, joins, aggregates, et cetera. There's also things like what the NoSQL movement is bringing to the table, et cetera. And then even cooler, if you're really into kind of the low-level geek stuff around these data structures and algorithms, things like flexible indexing, finite state transducers, these things can all free your mind up to do a lot of really interesting things. And so you should be thinking about how can I leverage those in your application. The last kind of 2 points on this really is this stuff is way more scalable than it has ever been in the past. And so you can take on the kinds of problems that you weren't able to do in the past, obviously, as evidenced by Twitter, LinkedIn, et cetera, et cetera. And then last but not least, one of the revolutions really going on in search is that this isn't your father's relevance anymore, right? So kind of in the older days of Lucene, you basically had one relevance model. And that was it. And if you didn't like it, well, you know, you could go maybe plug in some language modeling, or you could plug in something, but it was really kind of painful to do that. Well, now you can just plug in your own relevance, and what that allows you to do, for instance, is take in all of these other features, all of these other signals, and have those baked into the engine if you want them to be. So it gives you a lot more flexibility when it comes to scoring.
The evolution there is that we need to do large-scale analysis of human behavior in order to implement this reflected intelligence. We have to do correlation analysis. We have to say what occurred before and what occurred after, and find cases where those are interesting. There's an awful lot of coincidence in the world. It happens all the time, but some of it's interesting. You know, the old saying, first time happenstance, second time coincidence, third time enemy action. We need to find cases of enemy action where people say this, and then clearly, based on their further behavior, they mean that. Those correlations are what eventually let us reflect intelligent behavior from one person to another. And we can start with engineered knowledge and direct user feedback, but then we need to migrate from that to implicit observation of their behavior. And then at the large scale, we begin to find interesting features in the behavior, and we can start testing that, finding features that work, going forward with that, and those then lead to other features. And if we can test in a live system, the system can start learning on its own. It encourages behavior, it explores by providing opportunities to people, and then that lets us learn additional things, which become more and more interesting as the system operates.
How many people are doing regular experimentation? How many people are doing regular experimentation of relevance in their production systems? How many people just do kind of ad hoc within their organization? Most of the rest of you probably. Yeah, so this really kind of gets to that point about how we can start to use all of these pieces to do much more interesting things. So for instance, anybody doing actually tracking mouse tracks on the page as part of relevance? So you're looking at actual heat maps around where people are looking at when they show their search results. Anybody doing that? So there's one. I think this is another trend we've noticed with some of our customers, is you're starting to see more and more of those kinds of things. Talk about a big data problem. If you're actually tracking mouse tracks, you're going to be generating a lot of data across a lot of users. So with that, I think we're going to jump into some of the use cases. Ted, maybe you want to take the first one?
Yeah, I've got a question though. If people are beginning to do mouse tracking, how many people here are using brain implants to measure relevance? No, okay, not that yet, but I do say yes. So one of our customers, for instance, is very interested in using search-like technologies to find where flash mobs are about to occur. And the place where text-like data comes in is geolocated tweets. So they can see that people have a common theme happening in what they're saying. They can have a common geographical theme in where they're going. And then they can predict that there's something like a concert or a sporting event about to happen. People say fairly stereotypical things leading up to these events. And the key business value there is the ability on the part of the telecom provider to provision high cost things that are bandwidth that they don't want to have running all the time, but they can then provision in a few minutes when there's going to be a demand for that. They have microcells in stadiums, they have secondary data transports, things like that, that they actually have to pay to run, but which are critical to function during a disaster or during concert or during any sort of flash mob-like behavior. And so the idea here is to be able to predict in real time, based on textual and non-textual data, when they're going to need this sort of thing. Another example where you have this text-like information embedded in time, but it doesn't look like search so much on the surface, is a company in France that is augmenting ordinary advertising, ordinary television programming. And normally people say, oh, if you're just going to do untargeted ads on television, it's worthless. It's not as good as the internet because you don't know who saw it and you don't know what the reaction was. But it turns out there's one huge advantage to television, and that's time synchrony. Everybody who watches this broadcast has a very high likelihood of watching it at a very well-known time. And that means that they can look at social signals without a strong user-by-user cookie-type mechanism to identify who's looking, but they can use the time information to identify which parts of television programs, which ads are actually catching people's attention. And so they can then sell this reporting back almost as if it were internet advertising, and yet it's traditional, very high reach type advertising. And in several cases, they've been able to increase the value of the ads by 5x if they can augment it with these real-time derived metrics. But first they have to look at the text of things and decide what's happening. What references are being made? Are they positive, negative? Then they can produce these graphs that show here this part of the program was valuable, these ads clicked, and we can start doing time decorrelations to figure out who liked it and why. And then the ads are far more valuable because you can eliminate the losers and you can accentuate the positive, as they say.
I think another interesting one where you start to see search coming in is, this is actually a mutual client of ours who's been doing claims analysis, and they were doing a lot of interesting claims analysis before around fraud analytics, et cetera. But the big problem was that it was all data warehouse based, and it was taking them somewhere between 24 and 48 hours just to get basic questions answered around the data. Now, the kinds of questions they were asking, much of it was the kind of the case where you have a fraud analytics system in place, And that is really good at capturing some percentage of the fraud cases. But then you essentially need to have a human in the loop who can then go and look at the outliers, who can dig into specific cases and figure those things out. So in their old way, it was all data warehousing. They were doing these really massive SQL joins, et cetera, trying to essentially do search on the data. But what they were then able to do instead was take all of that data, all of the fraud analysis, all of the other signals that they were getting, hook that into a search system such that that information analyst, that fraud analyst, was able to then interact with the data in a very real-time mechanism, get back answers, click the facets, really drill in on the data, also have some BI tools driven off of search, off of their searches, as opposed to canned BI tools, which are driven off of whatever the IT department creates. And so they were really able to increase the speed at which they were able to adjudicate these fraud cases, their ability to decide whether this is fraud or this is not fraud, or whether this warrants other investigation by other people, so on and so forth. They were also able to then collaborate on those things with the other people on their team, so now they could start to get that reflected intelligence within the enterprise so that you can see what's going on. So it's not just one person's opinion. You have a way of sharing those things as well. This is one of my favorite use cases, mostly because it has a really nice humanitarian bent to it. We've been working with Virginia Tech for a while now on deploying our LucidWorks big data there and the underpinnings of this system, what we're talking about with reflected intelligence, into this really nice site where what they've done at Virginia Tech, one of the things that came out of the tragedy that happened there was a really interesting effort by a number of people in the Virginia Tech community to say, how can we learn from this? How can we help other people learn from these kinds of tragedies, these kinds of crises, et cetera, such that, hopefully we can either prevent them in the future or at least respond to them better, and then also help the people who were involved in it, the victims, et cetera, help them cope with what happened by perhaps getting them more information, et cetera. And so one of the things that they do is anytime there's some crises that's going on, they have a really nice relationship with the Internet Archive and a few other places where they essentially span out a bunch of crawlers, try to collect as much information as they can about some event, and then they bring it in-house. They try to make it searchable right away, because that's one of the key things to helping enable governments, et cetera, police, et cetera, deal with that data. How do you separate out the good from the bad? In those early, in the early parts of these kinds of crises, you want to be able to get people access to data as fast as possible. So obviously making it searchable as fast as possible, i.e. near real time, is really important. And then what they do over time with all of that data is they start to crunch through it. How can we enrich it? How can we learn from, how can we identify relationships in that data? How can we learn from those relationships? How can we learn from the context of the data, et cetera? And then also, how can we learn from what people are doing with that data? What are they searching for? What are they sharing, et cetera? And the end goal then is presenting out interfaces to all of these interested parties such that they can dig into that and hopefully learn from all that data and make for a better response in the future. Another really interesting application, I think, of search and reflected intelligence is really using this kind of system to catch the bad guys, right? So bad guys are often really dumb, and they're really sophisticated in some ways, but they're really dumb in a lot of other ways. And so what you can start to think about, again, is if you want to present an analyst workbench kind of situation where you can say to people who are looking for signals in data, you can give them a search interface, but then you can also supplement that with a lot of this reflected intelligence kinds of things. So in this particular case, a customer we were working with was looking at online drug counterfeit detection. So if you don't know it already, a lot of the online pharmacies, when they say they're selling brand X of whatever pharmaceutical out there, it often is not the case. It's often a counterfeit, because many pharma companies do not actually allow for online sales of their drugs. So those are often counterfeit drugs. So what you what we built with them was this kind of workbench where all of this data was coming in from crawls of online pharmacies, presenting obviously a search interface out to their analysts to allow them to interact with that data, and then looking to enrich it over time by trying to find and understand the patterns in that, such that you can find things like common phrases that people are using when they're selling things online around counterfeit drugs, et cetera, because oftentimes there's really subtle indicators in the language that indicate something is not quite right here. And so by giving that human in the loop, that search capability with this deeper machine learning aspects of it, you can get much more insight into what's going on.
So one of the common themes there is that in an adversarial situation, your opponent, if it's a fraudster especially, hopefully you're on the good side, the fraudster or the counterfeiter has a finite brain. All of us do. But these guys are trying to exploit as many opportunities as possible. So they have to slice their brain somehow. And if they can not just shard the brain but replicate it, then what happens is they can do more fraud. But the other thing that happens is they have more and more commonality in everything that they try because they're replicating, not just sharding. Or they wind up sharding and they can apply less and less brain to what they're doing, and so they wind up with fairly stupid things. So either way, the amount of information that they can actually generate, the amount of entropy that a fraudster can generate is relatively finite. And so if you can force them to reveal themselves through commonalities like this, you can beat them, or at least some large fraction of their attempts. And so this more like this comes to the fore as a key operation in here. But it comes into the fore anytime people can't put their full attention on something, or that they don't want to put their full attention on it. And so you see this in cases like the Music Match. Online Music was one of the first music recommendation engines. VO, we did video recommendations online. And what's happening there is people are doing something else. They're trying to satisfy their own needs. And what they do is they leave trails in terms of patterns. And that more like this type of operation is the key to finding those patterns. And so at VO, what we did is we built a large recommendation engine, and I'll show in a moment how we did that. But we put this large recommendation in there, and we took behavior type A and behavior type B. Type B is the sort of thing we're trying to encourage. In this case, it was watching videos. And type A is all of the other things that people are doing. And we found indicator behaviors in type A, stuck them into the search engine along the items of type B, so that when we saw people behaving these ways in these indicator fashions, we would know to pop up and recommend these item B sort of things. And in particular, I mean, these are kind of abstract descriptions there, we took terms that people put into the search box. And we took a relatively long history of that over a period of days or weeks. That was the type A behavior, the indicator behavior. The B behavior was which videos did they watch and seem to be engaged in. Did they watch for at least 30 seconds? And using the large-scale data analysis, we're able to find indicators. When they say this, they often want that. And the classic example was we had a test query, Paco de Lucia, that's a Spanish guitarist. We had no videos for that, but we did have people playing flamenco music. We had people doing flamenco dance. We had Van Halen doing classical guitar during a concert. We had other classical guitarists, Spanish and otherwise. And those were all excellent hits for that. And people would ask for Paco de Lucia, and they would eventually go watch these other things for other reasons. But those were excellent hits in a database that had no direct matches. And the metadata there was horrible because in many cases it was spammed, people trying to pirate videos. They would put them up with garbage metadata, then they would link from some other place. But then people would search on our system with what they wanted. They would eventually find it, some of them via the other way, and we could correlate the true search query with the actual video in spite of the metadata. This is kind of the antithesis of keyword search, where the keywords were so garbage you couldn't make sense of them. Here's mother's rhubarb, really it's Iron Man 3. How would you know? Well, you watch by behaviors. Another thing we did is we would put up logos on the website. So that's behavior A, clicking on that. And the first 20 or 30 people who would click on it would get a little under construction sign. After that, everybody who clicked got the recommendation for everybody who clicked. It's a self-fulfilling prophecy. Everybody who clicks, we give them what people who click want, which makes the website self-organizing. You click and you get what you expect. You put up cars and you typically get teenage boys. And what are they interested in? Girls in bikinis and fast cars. And they were thrilled with this category. So we could put up things that we didn't really understand, but somebody understood. Those people would click on it, and very soon, within minutes, the things that those people expected to see would be behind that emblem. It's an amazing sort of process, and it's truly reflected intelligence. The way we built that, did you want to talk about this? Or okay, is we would keep logs, and the logs would have a user ID, that's the first column. I just made these up in case you didn't guess. We have users 1, 2, and 3 doing stuff, and they have doing stuff to different things. Which things? In VO's case, it was videos, but exactly what they did and exactly what kind of things doesn't really matter. It's just that we have a record of users doing things embedded in time. And then what we do is we denormalize that a little bit, so we have a session for each user, the things that they did. Users are rows, things are columns. This is notionally a very large matrix. And using MapReduce, we can find the co-occurrences. So instead of users on the rows, we now have things on the rows and things on the columns. And so thing 1 appeared with itself 2 times. Well, you could define that as 0 or 2, whichever you like. But more importantly, T1 occurred with T3 twice. T1 occurred with T4 once. Now this isn't enough data, but if it were a lot more data, then we could look at each pair, say T1 and T3. Go ahead and click. And we could arrange the 2 that they occurred together and the 1 that T1 appeared without T3. See, it occurred with T4 once. And we could say T3 occurred with T1 twice and with something else once. I forget what else it occurred with, I think with T4. And then other things occurred with other things once. So we can build this little 2x2 matrix for every element in the matrix. And we can analyze this 2x2 matrix, and here's many examples of the 2x2 matrices, for which are the most interesting. And if you want to look at it yourself, you know, here in the upper left, A occurred about 1% of the time, 1.3% of the time that B occurred, and it occurred exactly 1% of the time when B did not occur. It's like, yawn, who cares? Same thing is true of B. So we put a low score on that. Here, however, A occurred with B 10 times and never occurred without it, and 100,000 other occurrences happen. That's beginning to be a big co-occurrence, a big surprise. So we put a big score on that. And so what happens is we then pick the biggest scores in any row of the co-occurrence matrix. So the co-occurrence matrix looks like this. We pick the biggest scores and we convert those elements to 1s. And that's all that's left. Each row, like the T2 row there, can then become a field in a Solr index. That field, here we just call it indicator. You might call it, you know, transaction tokens. Which merchants did you transact with? Query tokens. Which query terms are significant indicators for this sort of behavior? It's really pretty simple at that point. You do the co-occurrence, you find the interesting, the anomalous co-occurrence, and that provides you with stuff that goes into a search engine. A search engine, in fact, for a reflected intelligence system. And so we do MapReduce for the big data part, and we produce these item-item co-occurrences and scores, and then we have a search part where we export the interesting co-occurrences along with other metadata, maybe a geolocation if we're doing mobile restaurant recommendations, or the description and address, if you might have a location for that, or an offer ID, that sort of thing. And the search can take historical behavior, what have you done lately, and it can then position offers or recommendations for the person purely using one search for a polyvalent recommendation, including both search and historical behavioral metadata. You can even tune things like what's most popular on your website. You might as well, I mean, if there's lots and lots of most popular things, you might as well show somebody a most popular list that's canted just a bit toward their interests. It's still very popular items. It just has to be flavored dilutely with what you think is good. The people will like the most popular page much better that way. And then they'll start using the site more. And that's what we do. And then, of course, there's the question of how do you deploy this sort of thing? What sort of platform do you need? Well, you obviously need fast and scalable search. I think Solr when I hear that. You also need to have very large-scale storage and processing. Well, a guy with this hat on has to think MapR when he hears that. But those two work together. We just announced that we're doing a big partnership, and you can do the NLP sort of things. You can do all of these machine learning sort of things in a combined platform that way. Here's Grant to talk a bit about how that can be done.
So what we've seen, and this kind of architecture isn't just what we dreamed up in our spare time. I think we've seen this in a number of places, and in fact, in talking with a number of you in the audience that I recognize, there seemingly has come out of this a common reference architecture, I think, for this kind of processing, where, of course, you've got data coming in, you've got to go do your whole content acquisition things. There's lots of different tools out there, ranging from roll it yourself all the way up to really high-end ETL tools, etc. Tools like Storm, things like that for getting data coming in and dealing with it kind of as the speed of however you want to deal with it. And essentially what you're then doing is you're putting it into some authoritative store, nothing new here as well, right? Except for the fact that that authoritative store often these days is a whole lot larger. It's things like HBase or Cassandra, or I would posit, and I've seen from a number of you, something like Solr actually can be this as well. And so what we then try to do in these kinds of systems where you've got this, you need to have this very real-time component where users are interacting with this data all the time. Of course, you've got to have a search view of that, because that is the single best UI for that data for most users, because let's face it, we all know how to search. Not everybody knows how to write SQL statements or pig scripts, etc. So we're essentially trying to keep search in sync with our store here in real time or near real time, or if we're lucky enough that we have an engine that can power this at the scales we're at, then we just have, it's all a search engine, as Solr can be in many cases, right? And then you start to think about, well, what are all of the kind of things that I need around it? Well, you want the data to be in the right place at the right time, and that's what this store is about. So we've got our search going on, and then we can use tools like Hadoop, etc., to do this discovering enrichment side of the things. These are often large-scale jobs where you're crunching the whole collection, all of the logs, etc., etc. And when they're done, they update back into the store, right? And then you've got kind of all these peripheral services around it as well. So things where you're keeping your classification models, which aren't usually that big, but you need to be able to serve them very, very fast. You've got your personalization pieces, et cetera, analytics services, and then you put all of that behind a single set of APIs, because one of the things, another pattern that we often see when we look at this search plus big data problem is you go into most companies, startups, et cetera, what do you routinely see? You've got a bunch of developers who know how to deal with web services. They speak REST, they speak JSON, et cetera. They often don't speak Hadoop, they don't speak Pig necessarily, they don't speak some of those things. But yet they usually then have that one or two people on staff who do those kinds of things. And so by putting out those set of APIs on top, The application developers are happy because they don't need to worry about all this stuff that's going on down here. But the Hadoop experts, the machine learning guys, et cetera, they can still deal with all of these kinds of pieces. And so what this allows you to get is that virtuous cycle going where you have the best known state of the data being presented through search, and then you're really just working like crazy in the background using all of those computational nodes you have to enrich that best known state. Lather, rinse, repeat over and over, and now you have a reflected intelligence engine.
And then just one quick parting shot there. Of course, I got my MapR hat on. I think that MapR is a great platform for this. I don't want to belabor it. I'm happy to talk offline about that. But we provide a lot of the technologies that I've found over the years are required for systems like that. And then, of course, LucidWorks does the same thing.
Yeah, we do the search side of this, and so what we end up with at the end of the day, LucidWorks Big Data is our implementation of this. Using MapR down here at the bottom with LucidWorks, you have essentially this processing and storage layer where it's all about making sure the data is in the right place at the right time. You want it to be searchable when it's searchable. You want it to be in Hadoop when you need to do all of that. And then focus in on the search, discovery, and analytics layer. This is where you're enriching all of that, provide it up and out to the APIs, and then kind of all the rest of this stuff is glue that helps you run this in the real world. So there's some nice easy wins that come out with this kind of combination of things. Obviously things like analyzing logs. One of the cool things with MapR is, of course, you can just publish straight to any file system. It looks like a file system just like you're used to using. So just continue to write the logs the way you write your logs, and then you can analyze them in Hadoop, etc. You can also, of course, do things like store your indexes right in there, because all of your Solr indexing, etc., just still goes straight to the file system, etc. And then you get all of these other things like backups, etc. So at the end of the day,
that's it. 1 + 1 is 3. Search and big data techniques can really produce some very cool stuff together. You can, of course, contact us. I'm on Twitter, I'm on email, pretty much any email you can guess at MapR, at Apache, or at Gmail will work for me.
So with that, any questions? We've got some books to give away, so I think the way it works is the best question that you and I deem, we get to give away some books. So how about right there? So the question is when you're doing all this reflected intelligence, how do you deal with the fact that you have, in many cases, especially large-scale sites, you have way more votes than you can effectively deal with, and some of them may not be as good of votes as others.
Yeah, and there's a variety of techniques. At the first level, the LLR score does a very good job of getting rid of just garbage. Now, there are still some problems because some items are extremely popular. At VO, for instance, we had an intro video that everybody had to watch. They couldn't not watch it. So that's a really boring thing, and it appears on everybody. And so the item correlations for that are huge. You also have some crazy users. Again, at VO, it was our QA guys who watched every video because it was a bot and wanted to make sure that there was no error. And those people, of course, co-occur with everything that produces noise. As it turns out, for recommendations, or for any of the recommendation-like things, you can downsample items. The question is, how many users have to watch something before you understand it? 10, 20, 30, something like that. So let's keep 1,000 at most. How many items do I need to know that you've watched or interacted with or bought before I understand you? 10 or 20 is typically true. Let's keep 1,000. And so we downsample already at those two axes so that the data, the co-occurrences are bounded. The co-occurrence then is pretty easy. We do the co-occurrence testing and we get only the interesting things. But even then, we may have a lot of them, more than we want to put in there. Let's just keep the 50 or 100 or 200 biggest. And so by downsampling either randomly in the first two cases or by score in the final case, we get bounded, reasonable computations, reasonable index sizes. And there's been some nice experimentation at Technische Universität in Berlin, and they were able to show that this has unobservably small effects on recommenders, and that certainly has been my pragmatic experience as well. Nobody notices that you've downsampled this way. I love it. I love it. So the question is, I seem to be a Hadoop bigot, and what do I think about Storm, which is kind of real-time Hadoop or non-Hadoop or whatever. But the fact is, I love it. It does a very different thing than Hadoop does. Hadoop does a great job of analyzing a very long historical record, tens and hundreds of billions of events from the past. And Hadoop does that great, but that's historical, not real-time batch kind of things. Storm, on the other hand, does a great job of real-time processing. And in real time, you almost always have online algorithms with finite memory, limited history, but it's right now. So that's exactly the thing Hadoop does not do, and Hadoop does exactly things Storm does not do. Those are a great match if you can plug them together. And what you need to plug them together is a shared reference in terms of a file system.
I would add too, like one of the things as an example that we do, that we've been exploring with Storm is, so you do clustering in Mahout, for instance. It's a really large scale job, takes a long time, although Ted's been making it faster in recent memory with some new things. And then you always have this challenge of there's new documents coming in all the time, and well, which documents to those which clusters do those documents belong in? And so you can't obviously redo all of the clustering. So what you can do is use something like Storm as a way of computing the approximate clusters and then backfilling it back into Hadoop or into that shared file system, and then the next time it shows up. So it's that kind of hybrid system that allows you to do to kind of get the best of both worlds. How much time do we have?
There's no presentation after this.
So there's no presentation after. Great.
Never get out.
How about over there?
So the log likelihood ratio score intentionally looks for situations like that. So you have so the question is, when you have something viral, a lot of people watch it, why doesn't it connect to everything? And the fact is, it does connect to everything at the co-occurrence level. It connects to many things, but once you look for anomalous co-occurrence, then you lose those connections. And a great example is either the word "the," we've all said it today, sad to say, we all have said that, or the Beatles. If you get in an elevator, you probably listened to the Beatles recently. And the significant co-occurrence, the anomalous co-occurrence, is just not there for those words. So the question is about, can you use Solr for matrix exponentiation if it's doing matrix multiplication? But remember, first of all, it's doing matrix by vector, and it's only returning the top few hundred items. And so in a PageRank sort of computation, you want to propagate those low values because they could then reconcentrate at some far site. And if you're automatically pruning every intermediate state to the top largest values, you no longer have, strictly speaking, a PageRank sort of computation. Usually the most efficient way to compute PageRank is by using eigenvector type techniques. You do a singular value decomposition, and then you can exponentiate that very quickly. And those can be done with non-iterative solutions, which are more efficient for MapReduce type implementations. But catch me after, and I'll give you more details than you can stand on that sort of thing. Mahout has a very good implementation of that. So the question is about anonymous users. Do they come into this? Well, anonymous users come in two flavors. Anonymous users who you know who they are. They have an ID. And so we don't really care what the people's name is. Oops. Bad boy. Okay. And so, yeah, if you have sessioning for those anonymous users, they really just don't have a name, that's fine. You can also shorten the sessioning, so you churn the cookies so that they have more anonymity, but they can still contribute some co-occurrence information. And you could just throw those away and recycle on every few minutes. How many of the users do that? It doesn't really matter, because cookie killing is so rare that it doesn't really matter. And those people tend to have idiosyncratic things, like if you recommended to them, they would freak out. So it's probably better not to give them too any data anyway. Yeah, in the back. Yeah, so Mahout supports both singular value decomposition and sparsification techniques. In large data systems, sparsification via LLR is usually more efficient because it's one MapReduce or two or three to get those things, and then very simple tests. So you're just done. SVD is very good for smaller data sets. And by small, I mean something like the Netflix size with 100 million ratings. That's a small data set. At VO, for instance, that was about 12 hours of data. And the LLR becomes very useful in the implicit behavior as opposed to the explicit ratings. Ratings are far more rare than implicit behavioral observations. And so you use that there. But then the other characteristic is that SVD gives you dense matrices, the singular values, and those are not very suitable for use in a search index. We want to do this in a search index, so the sparsification techniques, which do give us searchable fields that are sparse and informative, are more appropriate for search-based recommendations.